Hi, so today is the first meeting of this course on nonlinear dynamics and chaos and its applications to turbulence and its statistical properties. So in the first lecture today, I'll be first giving a basic history and an overview of what nonlinear dynamical systems are and what are the ways of solving them. So I'll start by sharing my screen. All right, so here is a basic history of nonlinear dynamical systems and how it had all started. So dynamics was first invented by Newton with his laws of motion. So he had invented calculus and he had also solved the two body problem, which means that suppose you have one body of mass m1 and another body of mass m2 separated by a particular distance, then how would the dynamics of those two bodies evolve under their mutual attraction? Basically, what happens to the two bodies because of their mutual gravity. Okay, so he had solved the two body problem. Now, if you add a third body to this two body problem, then it becomes a three body problem. And then you see that if you write down the equations of motions, then it is impossible to solve the three body problem by hand. So this was where nonlinear dynamics first came into the picture. And then it was shown by Henry Poincaré that there are certain ways of approaching these problems, even if it is impossible to solve it analytically and exactly. So he had given a geometric approach for getting qualitative insights into such problems of three body motion, say for example. And with this geometric approach, it was possible for us to obtain a qualitative picture of how the system would evolve, which was not possible if we tried to solve it analytically. So this was where chaos first came into the picture. Then in the 1920s and 1950s, there were nonlinear oscillators, which was discovered in physics and engineering, basically with the invention of radio, radar, and laser, and all these things. And then also there was Kolmogorov, who had given his laws of turbulence, and also certain research into complex behavior in Hamiltonian dynamics by Arnold and Moser and all these people. But the main um, burst of chaos. I mean, the main research in chaos started in 1963 with the research of Edward Lorenz. So Lorenz was a meteorologist and he was basically trying to simulate the dynamics of atmospheric flows. So he had three equations. And when he simulated the three equations, then for a certain value of a parameter, he saw something very interesting. He saw that for two initial conditions which were almost similar to each other, their evolution after a certain point of time differed drastically. And then he realized that these two initial conditions were nothing but separated by the machine precision, the error due to computational rounding of error and all these things. So even when that happened, the solutions turned out to be very different after a point of time. And so he thought that he had trod upon something very interesting, and this is what we know by chaos. So when a system is chaotic, you no matter how close to say, initial conditions are, if they are different, then their ultimate evolution will also be very different from each other, and this is what characterizes chaos. And then after Lorenz's invention, there were many other many other breakthroughs in chaos, and notably one of the biggest breakthroughs in chaos was made by Michel Feigenbaum, which was the concept of universality. So he had shown that even if there are different systems which behave chaotically in different ways, there are certain underlying features which are common to both systems. And this is what is known by universality, and we will see this in this course when we study these chaotic maps and so on. And another interesting and important discovery, which was made in the 1970s and 80s, was the discovery of fractals by Benoit Mandelbrot, who was a French mathematician. So fractals are basically objects which have non-integer dimension. So you know, a paper has a two-dimensional structure, a line has a one-dimensional structure. The world we live in is three-dimensional. But fractals, they can have any fractional dimension, like they can be 2.5 dimensional structures or 1.2 dimensional structures and so on. So weird as it may sound, we will see that fractal dimensional objects are much more common in nature than one can even think about. So with this, we move on to some of the basic systems which uh, some of the basic nonlinear dynamical systems which have been researched upon and which are still being researched upon today also. So uh, on the left hand side downwards, you can see if in this table, as you go downwards, the system gradually goes from linear to nonlinear, and from left to right in this table, the number of variables in the system increases. So for a n equal to 1 system, for example, if you have an exponential growth or an exponential decay, like a radioactive decay, for example, and we will see in today's class that today's lecture that one-dimensional systems can exhibit fixed points which can be stable and unstable, and there can be bifurcations which we'll see in the next class also. And we will also give certain examples of where one-dimensional systems can be used for modeling real world systems, for example in population growths, in electrical circuits, in chemical reactions, and so on and so forth. Okay. Similarly, if you increase the dimensionality of the problem, the complexity also increases. For example, one can look at two-dimensional systems and a classic example of a two-dimensional system is a linear oscillator or a mass spring system. Why? Because a linear oscillator is characterized by two variables. In one, for example, a one-dimensional linear oscillator, it's characterized by two variables. One is the position and the other is its velocity. So you would see the equation of motion of an SHM, which says that x double dot is equal to minus omega square x, and this can be written as x equal to x dot equal to some velocity, and the velocity is equal to some acceleration. So that is how you can describe this system. Similarly, the two-body problem is another two-variable system, and so on and so forth. And two-variable systems can exhibit more complex properties like limit cycle oscillations, and which we will see in the upcoming classes as well. Now, chaos is mainly observed in dimensions 3 and greater. And why that is so, we will also see in the upcoming lectures, because it was due to a theorem given by Poincaré that chaos is not observed when the dimensionality of the system is below 2. So three-dimensional systems are very common around us, for example, in civil engineering and electrical engineering. And even Lorenz's work on where Lorenz had first discovered chaos, it was a three-variable problem. So it was a three-dimensional system as well. Similarly, you have the three-body problem, which I had spoken about a few minutes ago. And there are other three-dimensional systems which can be chaotic. And as you increase the number of variables in the system, the complexity increases further. And similarly, and for n much greater than one can have different kinds of collective behavior. For example, the flocking of birds. You have many migratory birds traveling together in groups, and you will see that they exhibit different kinds of patterns as they travel through from one place to another. So they describe different forms of collective behavior. Similarly, if you have bacteria growing in a particular culture or a medium, the bacteria collectively move from one place to another, again exhibiting many different kinds of patterns. So you see pattern formation and collective behavior when n is much greater than 1. And finally, every system that we see in the common world is a continuous system because time is continuous, right? Discretization is simply an approximation that we make. So when it goes into a continuum, then you will see that simple maps and stuffs are not enough, and one needs to take into account partial differential equations, which describes the system in terms of its spatial as well as temporal dimensions, and that is where the most chaotic systems come into the picture. For example, those in fluid dynamics and turbulence. Okay, so now that we have a basic overview of what chaos is and where chaos can be found, so let us turn to the basics now. What is a dynamical system? The short answer is that every system can be described as a dynamical system. Why? Because any system that you see around us can be described by this particular equation that dx dt is equal to fx. What is x? X is basically a variable which describes a certain property of the system. It can be the position of the system, it can be the velocity, it can be any other characteristic of the system. For example, it can be the energy of the system as well. And how x changes with time is governed by this function, which is f of x. Okay, so anything you see around you, that I mean, anything and everything basically can be described in terms of this equation. Therefore, everything can be modeled as a dynamical system. What are the ways in which we can classify dynamical systems? For example, here there are two ways in which we can classify, which will be helpful in our course. That is, one is an autonomous dynamical system, where the right hand side does not depend explicitly on time. The other is a non-autonomous dynamical system, where you see the right hand side, it explicitly depends upon this independent variable. For example, if you have a forced pendulum, where the external force is a function of time itself, then it turns out to become an non-autonomous system. Another classification one can make is the classification between linear and nonlinear. So if f of x is a linear function of its variables, then it is a linear dynamical system. And if it's a nonlinear function, then it's a nonlinear dynamical system. And by nonlinear, I mean anything nonlinear. It can be a quadratic, cubic, quartic, or it can be a special function also like sine, cos, tan, and so on and so forth. Okay, so then it becomes a nonlinear dynamical systems. Now, the question is, why are nonlinear dynamical systems difficult or at times even impossible to solve on a pen and paper? The thing is that if you have linear dynamics, then the linear systems can be broken down into small parts because each part is linearly independent of each other. And then we can solve those small parts one by one. And after that, we can recombine all of those solutions to give us the ultimate solution of the full problem. Right. For example, if you have, say, n number of balls which are just traveling around, moving around in your room independent of each other, and the equation of motion of each ball can be described as dx dt is equal to the position of the ball plus some acceleration, which is again a linear function of the position, for example. Then what happens is that if we have to know the collective picture, we can solve the equation for each ball independently, and then we can combine the solutions of all the balls to give the ultimate picture. Right. But what happens if the system is non-linear? For example, what happens if there is a coupling between the two balls? Suppose if two balls come together, then they interact by, suppose, their gravity. Or for example, if they are charged, then as they come close together, they have a Coulomb force which depends upon the charge on each ball. Right. So when that happens, then interactions come into the picture, and you will see that the system of equations will become a nonlinear equation. Right. In that case, you cannot break down the system into small individual parts, because what will happen then is that each part will depend on the other part. Basically, they'll be coupled together. So when they're coupled, you cannot solve each of them independently. So that is why nonlinear systems like these cannot be solved. Or in other words, the famous philosopher, I think Aristotle, had once said, the whole is greater than the sum of its parts, which basically describes the nonlinear systems in one line. Now, one depending on how one can model a dynamical system, it can be classified as maps and flows. What is a map? A map is a discrete in-time dynamical system. Basically, if you have a system in a certain state at right now, after 1 hour you again measure the system. After 1 hour you again measure the system, and so on and so forth. And you only have data stored in samples of 1 hour. Then basically you're having the data in a discrete manner. So a good way of describing the system over in, if you have discrete data, is to describe it in terms of maps. Okay, which says that the state of the system at the instant n plus 1 is a function of the state of the system at an instant n. Okay, and what are the real world examples of maps which we have? The most common example is a random walk or a Brownian motion, and other examples like stock markets, which can also be modeled in terms of random walks, are also examples of maps. And what is a flow? Flow is an exact opposite of a map. It is a continuous in-time dynamical system. Basically, anything and everything that we see around us, all classical systems are described by flows, because at the end of the day, everything is continuous, right? Discretization is something which happens when we make measurements on systems due to the shortcomings of our experimental devices. It is not possible to measure a system continuously, so it gets discretized. But actually, all systems are continuous in time, and therefore, it is ideal to model all of them as flows. And how do we model flows? We use ordinary and partial differential equations. So in today's lecture, we will study flows in one dimension, which is the simplest case of a flow. And we will see what fixed points are and how one can solve a flow, even if you are not able to solve the equation of a flow analytically, even if you're not able to find an analytic solution to the ordinary differential equation. All right. So let's move ahead with this. I will stop sharing the screen and I will share another screen. Okay, so let us start with a simple example of a one-dimensional dynamical system. All right. So suppose I have the equation x dot. Now when I say x dot, I basically mean dx by dt. This is equal to sine of x. All right. What is the solution to the system? Okay. So if we try to solve the system, then we can write dx by sine x equal to dt, and this, if we integrate both sides, we get t is equal to minus log cosec of x plus cot of x plus some constant c, and we can evaluate c if we put t equal to 0. So c is equal to uh, log of cosec x naught plus cot of x naught. Okay, where x equal to x naught at t equal to 0. So then the solution turns out to be that um sorry solution turns out to be t is equal to log of cosec x naught plus cot of x naught divided by cosec of x plus cot of x. All right. So the question is, how do we interpret the solution? Like, how do we find out x as a function of t? Well, it is not impossible to do it. It will require some insane mathematical tricks. But the thing is that this turns out to be very complicated, right? So then if somebody asks me the question that what will be the value of x at t equal to 3, I won't be able to say this, right? Because this is very difficult to solve. So what we can try to do is that we can try to get a pictorial insight into this problem. How do we do it? So what was the equation we had? We had x dot equal to sine of x equal to say fx, right? Now here basically the right hand side of the equation, it represents the rate at which x changes, right? It is the velocity of the point x. So let us see how the velocity of the point, it changes as a function of x. Okay, so if we plot x in this direction and the velocity, which is fx, equal to x dot along the y-axis, then it is simply a sine wave, right? Like this. So here I have pi, here I have 2 pi, 3 pi, 0, minus pi, 2 pi, and so on and so forth. Okay, so basically if my particle, if my x, that is x naught, initial position, if the x naught is somewhere over here in this place, right, then what is the velocity? Here the velocity is positive, right? The velocity is in this direction. On the other hand, if my x naught was over here, suppose, then here the velocity is negative in this direction. So if we plot this picture like this, we can actually see what the velocity in different points are, right? For example, in this position it is in this direction, here it is in this direction, here it is towards the right and left, and so on. So if my x is over here, it will move, x naught is over here, it will move to the right, and then it will come and sit at this point at pi, which has 0 velocity. Similarly, this x naught will come over here and sit at pi, which has 0 velocity. So you see the flow towards this point at pi, it is converging. And if x naught, if suppose that x naught was equal to pi, then basically the point would not move at all. Why? Because sine of x naught becomes equal to 0, which gives me x dot equal to 0 at x equal to pi. So at this point, the velocity becomes 0. So this is what we know as what we call fixed points. Similarly, you will see that sine of x is 0 whenever x is equal to n pi, right? So therefore, every fixed point, so the fixed points of my system x stars are basically n pi, where n can be any integer, right? Now, the next question is, we saw that the flow, it approached this fixed point from either direction. Can there be fixed points from which the flow moves away? Sure, they can be. For example, you look at this fixed point over here at 2 pi. You see the flow on the right hand side of 2 pi is towards the right, flow towards the left of 2 pi is towards the left. So this means that if we are slightly away from 2 pi, we will move away from it fast enough, and then we will go and sit at one of these fixed points. For example, we can come here or we can go there, which is another stable fixed point. Similarly, you will see that 0 is also a point from which the flow moves away. Minus pi is the point where the flow converges. Again, 2 pi is the point from which the flow moves away. So these solid circles which I have shown over here are basically stable fixed points, while the uncovered circles which I have shown over here are basically unstable fixed points, right? So you see, we had this very complicated problem in the beginning where we did find an analytic solution, but we did not know how to interpret the solution. Whereas if you draw a graph of this nonlinear problem, a graph of how the velocity of the point changes as a function of the position of the point itself, then it is easy to find out any solution. I mean, not the exact solution, but we can at least get a qualitative insight into how the solution might evolve. So this brings us to some of the terminologies which we should get well known, familiarized with as the course progresses. One is the concept of a phase space. What is a phase space? Phase space is basically the state space of a system. So for example, if the system is a 1D system, the phase space is the space of points of x and x dot, right? So basically, in a phase space, a point completely describes the system. So here we have the 1D system, which is described completely in terms of its position and velocity. So if we draw a graph of x and x dot, then this graph becomes a phase space of this one-dimensional system. Similarly, if you have a 2D system, then the phase space will be comprising of x, y, x dot, y dot. So you see here the phase space becomes actually 4-dimensional. Here it was 2-dimensional. So therefore, if our system has n variables, right, then each variable is described by its position and its velocity, then the dimensionality of the phase space will be 2n dimensional, right? So it will be a 2n dimensional phase space. So the concept of phase space is very important when it comes to analyzing nonlinear dynamical systems, because as you saw in the previous example, by drawing the phase space, we were able to simply and very easily find out how the system will evolve from one point to another. And now, once we have described the concept of phase space, now comes the concept of fixed points, which we had seen only a few minutes ago. Okay, so what are fixed points? Fixed points are basically the locations where the flow velocity is 0, right? So if x equal to x star is a fixed point fp of x dot equal to f of x, then f of x star is equal to 0. So this is the equation which helps us to find out the fixed points of a system. And fixed points can be both stable as well as unstable. So previously we had seen from the diagram how to classify stability. We will do a few more examples with diagrams only to classify stability. And once we have got a good hold on this, we will try to analyze stability with the help of mathematics. Okay, so now coming to the classification of stability with the help of diagrams. Okay, so suppose I have a system. Example, suppose we have x dot equal to x square minus 1. This is my fx. So what are my fixed points of this system? So basically to find fixed points, I have to have f of x star equal to 0. Right. So then this means that I have to solve the equation x square minus 1 equal to 0. This has two solutions. So my fixed points are basically x star equal to plus minus 1. All right. Now let's draw the graph. So what will the graph of this function look like? This graph will look something like this. It will be a parabola, quadratic function. This is my f of x. This is my x. This is the origin. This is plus 1, which is the fixed point where f is, and this is minus 1. Okay. So here f of x is above the x-axis, right? So the flow in this direction will be towards the right. We can mark it like this. Here f of x is again positive. Here the flow is towards the right again. But in this portion, the function is negative. So here the flow is towards the left. So what does this tell me about the fixed points at minus 1 and plus 1? The flow is always away from the fixed point at plus 1, right? So it's an unstable fixed point. On the other hand, the flow is always towards the fixed point at minus 1, so it's a stable fixed point. So simply we have calculated this equation, and we have we have solved the equation, and we have found the stability of fixed points. Now let us take a look at some systems of practical interest where we can apply this knowledge. You will see that you have come across these systems in your higher secondary school as well as bachelor's also. So one practical example is an electric circuit. Okay, let us draw the electric circuit. You have the resistance R over here, and you have a capacitor C, and there you have the voltage. Okay, here's the battery V0 plus minus, and you close the circuit like this. Okay, so if you apply, what is the voltage drop across the resistance and the capacitance? If I is the current, then the voltage drop is basically IR plus Q by C is equal to V0. Right. Now I is basically Q dot. This implies that Q dot is equal to V0 by R minus Q by RC. All right. So then this is the equation of my dynamical system. This part is basically f of q. So what are the fixed points of this system? So what we can do is that we can again draw a graph like this. Okay, and we plot f of q as a function of q. All right, what does this look like? So this basically is a linearly decreasing function of q, and this is the point where it intersects the x-axis, and so this is the fixed point over here. So this point is basically q equal to q star. And what is the stability? Is this a stable fixed point? Well, sure it is, because here the flow is negative and here the flow is positive because f is positive, and therefore it is a stable fixed point. And you will see that interesting, what is the value of q star over here? To find q star, you put f of q equal to 0. When you do that, you will see that q star in fact turns out to be equal to c into v naught, right? So in the steady state, the voltage drop across, this is the total charge which accumulates in the capacitor. And this is a logical thing, right? Because if you're charging a capacitor with a battery which has a potential difference of v naught across it, if initially the charge was 0, it will accumulate and go up to v naught, right? Sorry, cv naught. That will be the total charge stored on the capacitor. So this was something which we already know earlier, right? Now the interesting thing happens. What if we have a nonlinear resistance? So suppose we, if for a linear resistance, R is basically proportional to V for a constant I, right? So if the resistance is nonlinear, for a nonlinear resistor, we can have R is, say, some function g of V, where this is a nonlinear function. And you will see that equations like this, these are especially important in semiconductor physics, where you can have nonlinear resistances. So then this particular equation of q naught, this could have been solved by hand if it is linear, right? But now when it becomes nonlinear, then how do you solve this equation? That is the question. Okay, so let us say that this function g of v has this particular form. Okay, g of v, and this is v. So then what will be the fixed point of the system? So then the dynamical equations, first of all, it will change. So q dot becomes equal to mm, hold on. Sorry, I made a mistake over here. Um, so when we have a nonlinear resistance, then it's not the, so when we have a nonlinear resistance, it is the current through the resistance. So initially we had I equal to V by R, right? And now what happens is that in this case, I becomes a function of V, and this function is a nonlinear function, right? So then in that case, how does this picture change? So basically I is equal to now q dot, which is equal to g of v. So what happens is that, for example, say g of v has this particular form. Okay, so then dq by dt is equal to this equation over here. and therefore the fixed points of this equation are given by basically g of v equal to 0. So this is the fixed point of this particular equation. And what is the stability of this particular fixed point? You will see that this point is entirely unstable. All right. So how do we interpret this? This basically means that the voltage across the capacitance would go on increasing indefinitely in either direction, right? And this seems to be an unphysical solution. So what this tells us is that nonlinearity can introduce different kinds of problems into some problems which we had been able to solve linearly using basic examples. All right. Another interesting example which we can try out is basically this: x dot equal to x minus cos of x. So what are the fixed points of this equation? So to find out fixed point, we must have fx equal to 0, which means x equal to cos of x. Now this equation, it is impossible to solve by hand because it is a transcendental equation. All right, so one interesting way to solve this equation is to do it graphically. So you plot a graph like this, and then you plot on this graph the function cos x. This is cos of x, and you also plot this function which is x. All right, so you will see that if you do it correctly, then there is only one point of intersection between x and cos x, and this is the point where basically x is equal to cos x, and this is the fixed point. All right, so this turns out to be my x star. Now we have to see whether the fixed point is stable or not. How do we do that? So we have to analyze this function f of x, which was x minus cos x, right? So on the right hand side of this fixed point over here, what happens is that x is greater than cos x, which means that f of x is positive. So the flow here is away in this direction, and on the other side here we have f of x is negative because x is less than cos x, so the flow is in the left. So what happens is that the fixed point here is an unstable fixed point. Okay. So here also the important thing is that even if you can't solve the equation for the fixed point itself by hand, by simply drawing this graphical picture, you can get an insight as to where the fixed point can be and what its stability might be also. Right. So now we move on to a realistic model, which is a model of population growth. So basically, how can one model a population growth? Suppose you have n number of individuals at a given time. Those n number of individuals, they reproduce and then they give rise to a larger population. So let us say that n of t is the number of individuals at time t. Okay, and what does this depend on? One can say that it is proportional to n itself, because the size, if you have unlimited number of resources, then there are enough resources for everybody in the population to reproduce and give rise to the next generation. So the size of the next generation will be linearly proportional to the number of individuals in the current generation, and this turns out to be a very simple model for population growth. So if we denote the constant of proportionality as R, then we have, um, sorry, it's not the number of individuals, but dn by dt, the growth rate of the population. The growth rate of the population is proportional to the number of individuals at a given instant, right? And then, so then the population model can be written like this. But the thing is that, is this a correct model of population growth? This states that the population will keep on growing exponentially forever. But this is not the case in real world systems. Why? Because as the population grows, the the resources in the environment get depleted, and as the resources get depleted, the growth of the population should get lowered and lowered, right? So there needs to be some controlling factor for the growth, which is given by the limited number of resources in the environment. So basically, the what that means is that the growth rate of the population at the current instant should be proportional to the number of individuals multiplied by minus nk. This is, mind you, it is a very simple model, and it's basically a simplification. What this means is that, let us see what this means. So when n is less than k, then dn dt is a positive quantity, right? Which means that there is growth. However, when n becomes greater than k, then this term 1 minus n by k becomes negative. In that case, dn dt becomes less than 0, which means that there is decay when n exceeds k. So it appears that when n is below k, there is growth. When n is up above k, there is decay. And so it appears that the population size will tend to approach k, right? So this is what is known as the logistic equation, which was one of the first proposed models of population growth. And it was also able to represent the growth of small populations of bacterial colony very accurately. So here is the logistic equation, one of the basic models of population growth. But mind you, it does not hold true in every case, because there are always certain deviations, and there always needs to be improvements over this model, and it is still an active field of research as of now. So let us analyze the stability of the fixed points of the logistic equation, for example, and let us see if it gives us useful pictures into the dynamics of population growth. So here f of n is basically Rn into 1 minus n by k. So then the fixed points of this equation, f of n star equal to 0, which means that n into 1 minus n by k should be equal to 0. And therefore, we find that there are two fixed points of the model, n star equal to 0 and n star equal to k, as we had thought of earlier. Now let us plot a graph of f to see what it actually looks like. Okay, so here you have f, here you have n, we have f0 at, and here you have k. So between 0 and k, f is positive, right? So, and it's a second order function of n, so it should be a quadratic. So it looks something like this. Okay, so here is one fixed point. So there are two fixed points, one at 0 over here, at 1 at n equal to k. And now let us analyze the stability. As you can see, you can also continue this here. So as you can see, f is positive in this part, negative in this part, negative in this part. That means that the flow is always away from the fixed point at 0, which means that 0, n equal to 0 is an unstable fixed point. and n equal to k is a stable fixed point. Now, what do we mean by fixed points over here? Basically, it means that if the number of individuals at time t equal to 0 were 0, then d and dt will be 0 forever, which will imply that n at t will be 0 for all t. This makes sense, right? Because if there are no individuals at t equal to 0, the population will never grow. It can't grow out of thin air. Now, if n is slightly greater than 0, then what happens is that there is exponential growth. N grows very fast until it reaches this point over here, which is equal to k by 2. So when n reaches this point k by 2, its growth rate f slows down by, because the maxima of fx, how do we find the maxima of fx? We can find df by dn, which is equal, f was this thing over here. So df by dn turns out to be 1 minus n by k minus 1 minus n by k and n common minus n by k equal to 0, right? So from this we get 1 minus 2n by k equal to 0, which implies that n should be equal to k by 2. So this is the point where f is equal to f max. This is the maximum growth rate point. Beyond this point, the growth rate gradually decreases because f is decreasing over here. So the growth slows down beyond this point, and finally it becomes stabilizes as it approaches this fixed point. So one can also plot a graph of the growth rate like this. So at time t equal to 0, at t equal to 0, basically the growth rate this is the growth rate which was initially at n equal to 0. This is the maximum growth rate, which is equal to r, and as you go ahead and ahead, it goes up down like that. And at n equal to k, again the growth rate is 0. Okay. So one can also plot the number of individuals as a function of time. So how does this change? How does n grow as a function of time? We know that this is a fixed point and n equal to k is another fixed point over here, right? So if the population was at k or population was at 0, it won't grow with time. But if it is somewhere in between, then it will grow with time. And let us mark the point k by 2 over here. So suppose the population was initially over here, somewhere over here, it will start growing rapidly towards this point. But once it reaches this sort of value of k by 2, the growth rate decreases and it gradually approaches this point. Similarly, if you start from some point above k by 2, the growth rate will always be decreasing like this as it approaches this carrying capacity. And from the top, it will always go like this and approach the carrying capacity. Okay, so this basically gives us very useful insights into the logistic model and tells us how the population can grow for a given initial value of the total population. Right. We can also look at a more complex examples of population growth. For example, we can look at this problem called the alley effect. What is this? So what alley effect states is that for certain organisms, the effective growth rate, which we denote as n dot by n, this is the highest at some intermediate value of n. Okay, which means that basically at some mid-range value of n, where n this is 0, this is infinity, value of n in between 0 and infinity, the growth rate is the highest. And this physically means that when the population is very small, then it is very difficult to find individuals for the organisms to mate, and therefore the growth rate is small. And when the population is too large, then there is competition due to limited number of resources, which is why the growth rate is also small over here, but it peaks at an intermediate value of n. Okay, similar to what we saw over here. Here also we saw that the growth rate, that is the right hand side, it peaked at an intermediate value of n. Here it was small, here it was small. Right. So another model which can describe such intermediate growth rate is something like this, equal to r minus a into n minus b whole square. Okay, where r, a and b, let us say these are constants. Okay, so basically this means that dn by dt is equal to n into r minus a into n minus b whole square. So what are the fixed points of this system? The fixed points are again given by f of n equal to 0, which means that n into r minus a into n minus b whole square is equal to 0. So again, one of the fixed points is n star equal to 0. The other fixed points are given by r minus a into n minus b whole square equal to 0, which means that n minus b is equal to plus minus root over r by a, or in other words, n star is equal to b plus minus root over r by a. Okay, so then if you plot a graph of f of n as a function of n, then you can clearly see the fixed points. What are the fixed points? There can be many different of them. Suppose we have one case where a root over r by a is greater than b and r and a are both positive. Okay, when this happens, then what we see is that there can be one fixed point over here, one fixed point at 0, and one fixed point somewhere over here at this negative value of n. And what will be the value of f of n at these points? F of n is basically given by n into r minus a into n minus b square. All right, so when or I can write this as n by n into a r by a minus n minus b whole square. Right. So when so basically you need to analyze this function over here as I had shown you earlier, and then you need to find at which points f of n is greater, at which points f of n is lesser. And once you get the curve of f of n as a function of n, you can basically trace to which fixed points the flow would go to. So you can try this question as on your own, and I will show you something similar in this class as well. So we had seen till now that given a system of equations, I was able to construct the graph of f of n versus n, and from this I was able to find the qualitative nature of the flow. Now let us see whether things work the other way around. Suppose I know the qualitative nature of the flow, I know what the fixed points are, I know how the flow goes. Is it possible for me to derive an equation for the flow? So here's where real world modeling comes in. In the real world, we know we do not know what the equations governing the system is. We only have the data, right? And from the data, we need to find out the equation which models the particular system. So this is how modeling works. So for example, I can give you an example over here. You have the line like this. You have one fixed point over here, one fixed point over here, and one fixed point over here. Okay, this is the y-axis. This is a stable fixed point. This is an unstable one on the right. And this fixed point over here, this is what we call a semi-stable fixed point. That means it is stable from the left hand side but unstable from the right hand side. Okay, suppose this is at -1, this is at 2, and this is at 0. And the flow looks like this, basically. Okay, right. So if my flow looks like this, and I have fixed points over here, then what is the equation that I have? Then I have to first map this onto f of x. Okay, so if I have to, this is my x. Now if I have to draw f of x on the basis of this, so what will f of x be? The first thing that we know is that at this point it is 0, at this point it is 0, and at -1 it is 0, because these are the fixed points. 2, 0, -1 of the fixed points, so f of x is 0 over here. Okay, now in this particular interval the flow is towards the left. That means here the f of x should be negative, and here f of x should be positive because the flow is towards the right. In this interval again the flow is towards the right, so f of x is positive. Here also flow is towards the right, so it is positive, and here the flow is 0. So what is the functional form of fx that can satisfy this? So basically f of x will look something like this. It will look like, go from here like that, and then you will have something like this. Basically it will come up here, it is positive here, but it has to go down to 0, so it will go like that and again go like that. So this is the particular form of f of x we have. So you see this is the form of f of x, and which order of polynomial can have this particular form? There are two minima, right? One minima over here and one minima over here. So it is basically a biquadratic. So basically I can model f of x as a biquadratic equation, which means f of x is equal to a into x to the power 4 plus bx to the power 3 plus cx plus t, the most generic form of a biquadratic equation. And from this we can actually tune the parameters a, b, c, and d. And once we tune the parameters to this particular form, either analytically or by other means, we will be able to generate the functional form of f of x, and this will be equal to dx dt. So this is how we can model the particular system given the initial knowledge of my fixed points. All right. So from the fixed points, you were able to model the system. Now let's see another way of going backwards from the initial solutions itself. Okay. So suppose I have solutions like this. You have 0, -1, 1 over here. So basically this is one solution. This is one solution. This is again one solution. And this is one solution. So how do you model the system? So the first observation that we make is that there are two fixed points. Why? This is one fixed point and this is one fixed point. This is a fixed point because the flow does not move away from this point, and it seems to attract the flow from all other points from -1 and also from above it. So this seems to be a stable fixed point. On the other hand, this fixed point over here at +1, this seems to be unstable because the flow away from it gets repelled away from it. Right. So basically, if we plot a graph of f of x as a function of x, then you will see that there is one fixed point over here, which is a stable fixed point, and the fixed point over here is an unstable fixed point. Right? We get this from here. So basically, this means that the flow is in this direction over here and in this direction over here. All right, that means f of x should be negative here and f of x should be positive here. So this tells us that, and another important thing is the shape of this. You see over here, here it was increasing and then all of a sudden it is decreasing like this, right? So this means that the growth rate, or the decay rate from 1 to 0 is fast over here, but fast in this portion and slow in this portion. So there is only one inflection point, which is around here. That means that if f of x is negative in this interval, true, but it will only have one minima. It cannot have more than one minima, which means that there will be multiple inflection points. So the only form which f of x can have over here is something like this, which is a parabola, right? So this is the form of fx, and an example of this we had already seen earlier, which was x dot equal to x square minus 1. So this is one equation which satisfies this. Sorry, I think I made a mistake in writing this equation. This is not the equation, because the equation which satisfies this particular form is actually f of x equal to x into x minus 1. Therefore, the system is this thing. Yep. So this gives us a basic insight into how to model a real world system in terms of a dynamical system given the initial data. Given the experimental data. Okay. So now that we have seen how to handle things geometrically, now let us take a look at a mathematical aspect of what stability analysis actually is. So what are we doing over here? We are actually seeing how an initial point moves away from approaches a fixed point. Another way of stating this problem is that suppose I am perturbed slightly away from a fixed point, then will I move close to the fixed point or will I travel away from the fixed point? And if I do either, then how fast or how quickly will I move, how fast or how slow will I go towards or travel away from that fixed point? So mathematically, this can be answered with the help of linear stability analysis. Okay, so let us suppose that x equal to x star is a fixed point of the system x dot equal to f of x. Now let us suppose that eta is a small perturbation away from x star. So we can write x at any given time as x star plus eta, which is a function of time. And then how does this x particular point evolve? Xt is basically equal to f of x star plus eta, right? F at the given value of x. Now since let us assume that eta is much smaller than x star. Okay, so then what happens is that we can expand this in the form of a Taylor series. And what is a Taylor series? F of x star plus eta, I can write this as f of x star plus eta into f dashed at x star. When I say f dashed, I basically mean df dx plus eta square d2f dx square at x equal to x star plus higher order terms eta cube and so on. So we can basically make this Taylor series expansion. All right. Now what happens? This term is 0 because x star is a fixed point. So we have f of x star plus eta equal to eta into f dashed of x star plus higher order terms, which we denote as terms of order of eta square. So this notation basically represents terms of order eta square and so on. So up to first order in eta, so we can neglect this. There is a condition for neglecting this term if eta or f dashed x star is much greater than order eta square. When this happens, we can neglect this term. And so to a first approximation, let us suppose that this actually happens. Then basically we have f of x star plus eta is equal to eta f dashed at x star. Okay. Now the left hand side, this is nothing but d dt of x star plus eta, and x star is a fixed point, so d dt of x star is 0. So this is basically equal to d eta by dt, or in other words we have d eta by dt is equal to eta into f dashed x star. And if we solve this equation, we get eta as a function of t is equal to eta 0 into exponential of f dashed x star into t. Right. So this particular equation basically tells me whether my perturbation about the fixed point eta will grow or decay with time. So what happens if f dash of x star is greater than 0, then eta t will grow with t, right? This because this represents an exponential growth. On the other hand, if f dash x star is less than 0, then eta t will decay with respect to time, right? So in this case, perturbation grows with respect to time. In this case, the perturbation decays with respect to time above the fixed point. And therefore, from if you try to map this with the earlier picture on fixed points which we had shown, you will see that this corresponds to a unstable fixed point, and this situation is a stable fixed point. So this is what stability analysis is all about. So basically we did all this calculation to see how the perturbation grows with time, and you see that the condition for the growth of perturbation is simply contained in the derivative of the right hand side of the dynamical system, right? So basically in one statement, what does linear stability analysis say? That for any fixed point x star of x dot equal to f of x, if f of x star is greater than 0, x star is unstable. If this thing is less than 0, x star is stable. Now here comes the catch. What happens if f of x star is equal to 0? Then if f of x star is truly equal to 0, then this particular assumption will no longer hold. Sorry, f dash of x star. If f dash of x star is equal to 0, then this assumption will no longer hold true, and then we need to look at higher order terms in the Taylor series, and we will see examples of where this can be applied. So for example, the simplest case for which we had done the diagrammatic thing and all these things, we can show that, for example, you have x dot equal to sine of x. So here f of x is equal to sine of x. Then what are the stability of the fixed points? So we have f dash of x is equal to basically cos of x, right? And we had x star equal to n pi, which were the fixed points, which means that f dash of x star is equal to cos of n pi, right? Therefore f dash of x star equal to what? Plus 1 if n is even, minus 1 if n is odd. So this basically means that this is the unstable fixed point and this is a stable one. All right. So if you try to map this with the diagram which we had drawn earlier, you will see that this is exactly true. So these were the unstable fixed points, and the unstable ones we get when n is even, 2 pi 0, 2 pi 4 pi and so on. And the stable fixed points pi, minus pi, 3 pi and so on we get when n is an odd number. Right, so you see, by doing stability analysis you can simply find out the stability of a fixed point. Okay, and one more thing which I should state over here is that you can also find out the characteristic time scale of decay of perturbations. Why? Because we saw that the perturbations eta of t, they grow as eta 0 exponential of f dash x star into t. So for example, if I tell you to, if one wants to find out the characteristic time scale, that means the time scale at which the perturbation grows to e times or one, or grows to e times or decreases to e times its 1 by its original value, then the characteristic time scale t c can be written as 1 by f dashed of x star. So this basically tells me that if f dashed of x star is a large quantity, that means if the perturbation grows very rapidly away or very, if the perturbation grows very rapidly away or comes close to the fixed point very rapidly, then the characteristic time scale is small. On the other hand, if the characteristic time scale is large, then the perturbation decays or grows very slowly. Okay, now let us turn to some of the special cases when f dash of x star is equal to 0. So for example, consider the following equation, that x dot equal to um, minus x cubed. Okay, here what do we see? F dash of x star is equal to 0. X star is basically equal to 0. F dash x star is 0. F double dash x star is also 0, and f triple dash x star is equal to 3216 minus 6. Okay, so this means that if we do the Taylor series expansion, it basically turns out to be like this. You have f of x star is equal to 0, f dash x star is 0, and the second derivative is also 0. So you have basically 1 by 3 factorial eta cube f triple dash at x star, and this turns out to be equal to minus 6 by 6 eta cube. Okay, and now if we were to like do the stability analysis for this problem, this is nothing but eta dot over here. So this means that eta dot is equal to minus of eta cube. And what is the solution to this? D eta by eta cube is equal to dt. So minus 2 plus 2. So this is basically 1 by 2 eta square is equal to t, or plus some constant c, or in other words, eta is equal to 1 by square root of 2 into square root of 2 into t plus c. So an interesting thing which we observe over here is that the perturbation, first of all, is it a stable or an unstable fixed point? That we have to find out first. So basically, um, because eta dot is a negative function of eta, so this basically tells me that the so basically this particular equation, it tells me that as time t goes to infinity, eta as a function of time will grow to 0. That means the perturbation will decay as a function of time. So this tells me that the fixed point x star is a stable fixed point, right? Because the perturbation is decaying as a function of time. And how is it decaying? At very late times, when t goes to infinity, eta t scales as t to the power of minus half. So you see, this is an algebraic decay. Algebraic decay. And when we had analyzed the system earlier using linear stability analysis, we had found that the growth and the decay is an exponential function. So this is an example of a nonlinear stability, nonlinear stability analysis, right? Because nonlinear stability analysis now gives me an algebraic growth instead of an exponential growth. Similarly, you would see that instead of minus x dot, if x dot was equal to plus x cube, then we will also see an algebraic growth, and the fixed point will be an unstable fixed point. So I don't do this calculation over here. I leave this for you to do. We can also see another interesting example of a fixed point, which is not stable and unstable, but a semi-stable fixed point. So suppose you consider the equation that x dot equal to x square. Okay. So then if you again do linear stability, x star plus eta is equal to, we keep only the second order term, eta square by 2 and f double dashed of x star, which is nothing but 2. So this is equal to eta square. Therefore, eta dot equal to eta square. Okay. So this means that d eta by eta square is equal to dt, or minus 1 by eta is equal to t plus c, or in other words, eta is equal to minus 1 by t plus c. Okay. So if you see that now eta is now the fixed point x star was equal to 0, and eta is a small quantity which is just greater than 0. Okay. So if eta is positive, eta at t equal to 0. So what is c? First we need to find out the constant c to do this analysis. So basically c is eta at t equal to 0. So c is equal to minus 1 by eta 0, which was the initial value of the perturbation. Then we have eta equal to minus 1 by t minus 1 by eta 0. Okay. Now if eta 0 is a positive quantity, then and if eta 0 goes to 0, and if eta, that means that 1 by eta 0 goes to infinity. Okay. Now if so therefore if eta 0 is greater than 0, that means it goes to 0 from the right hand side, then t minus 1 by eta 0 is again a negative quantity, which means that eta turns out to be positive. That means the solutions will grow from the right, and If eta 0 was negative, the other thing will happen, and then in that case, if eta 0 was less than 0, then you see that eta turns out to be negative as a function of time. In other words, this particular equation has this form of the graph of f of x as a function of x. Okay, so here is f of x, here is x, and now you will see that this particular fixed point over here, the flow in this direction is towards the right, here also it is towards the right, and this part is the stable part and that part is the unstable part. Okay, so it's a semi-stable fixed point. So you see that linear stability analysis gives us useful insights into the stability and instability of various kinds of fixed points. Okay, so since this is introductory lecture, the first lecture of the course, I will stop over here, and I will continue on for the rest of the lectures in the next part. So in the next part we will see how to do, so in this part we have seen how to graphically solve equations and study a system, and then we have also seen how to do linear stability analysis to find out the stability of fixed points. And when linear stability analysis does not work, then one needs to do nonlinear stability analysis as well, and then you see algebraic growth and decay away from fixed points and so on and so forth. So after this, we will do this theorem known as the existence and uniqueness theorem, which tells us the conditions under which one can have a solution to the system of dynamical equations. And after that, we will move on to bifurcations and so on, and bifurcations of fixed point, which itself is a very interesting topic with great physical relevance. So I will stop over here and we will continue on from the next lecture.